In this video, we're going to look at one of the key properties that we associate with straight lines. Namely, we're going to focus on the gradient aspect of lines. Now, when we're working through the material at a higher level, there are several properties of the gradients of straight lines we need to be able to work with and use to answer slightly more complex and intriguing questions. To start with, let's remind ourselves what the gradient of a line is. So, the gradient of a line has a simple meaning. What it refers to is the slope of a line. So it refers to how sloped and steep the line itself is. And there were a couple of different types of gradient we came across. So we came across lines that had a slope like that. We came across a line that maybe had a slope doing this. And we came across flat horizontal lines, and we came across straight up vertical lines. The lines that went up from left to right, we said had a positive gradient. So as they were going up in x, they were increasing in y, so it went up. Lines that were going down from left to right, as in this case here, had a negative gradient or a negative slope. So as they were increasing one, they were decreasing in the other. This flat line here had no gradient. There's no slope, there's no change in the y values. It's fine. And this line here going straight up and down, there's no change in the x, but it's going up and down. There was no gradient, so we said the gradient of this line was what we call undefined. So it had no associated gradient with the line at all. Now, when we were working with the gradient, we remember that we needed 2 points to calculate it. So we take any two generic points, let's say a point A and a point B, and we can calculate the gradient between these 2 points using the formula for the gradient m equals y2 minus y1 over x2 minus x1. This gave us our general formula for the gradient of a straight line. This is what we've been using up to now. However, there is another version of the formula. So again, if we stick to just two generic points, A at x1, y1, and B at x2, y2, and we plot them, we'll see what I mean. So imagine we take the 2 points A and B, and we just generically plot them somewhere on our grid. So there's my point A, there's my point B. And that's the line that joins the two of them together. Now we know gradient, y2 minus y1 over x2 minus x1, is vertical distance over horizontal distance. So imagine we complete that by, again, turning it into a right-angled triangle and looking at the vertical distance here and the horizontal distance here. Vertical distance we got by doing y2 minus y1, and horizontal distance we did by doing x2 minus x1, which gave us our gradient, our vertical change over our horizontal change. Now, we're able to approach this in a slightly different way as well. If we were to name the angle theta, what we're able to do is approach this using trigonometry to actually find a way of getting our gradient and the way our line slopes. Because if we think of this as a right angled triangle, and we use basic trig on it, so using our SOHCAHTOA, this is the angle theta, this is our opposite and our adjacent. What that means is we're able to take the tan of theta and get our opposite over adjacent, so get our vertical, our y2 minus y1, over x2 minus x1. Gives us the exact same thing we're looking for. This then allows me to say that I can also calculate the gradient by taking tan of theta. But where we get theta is the key thing. Theta has to come from the counterclockwise direction from the x-axis. So you imagine there's my x-axis, there's my y-axis, there's my line there, there's our angle theta, and it has to come from a counterclockwise movement up from the x-axis. If we were to be given the angle here on this side, we'd have to do 180 degrees, the full turn, take away this angle to get the theta. Using this, I can get a new version of the gradient of my straight line. So, let's look at a couple of examples of that. The first example, what I'm going to do is give you a wee scenario, a wee drawing. So let's imagine we plot a line here, and I tell you it looks something like that, and I've got an angle there, it makes an angle of 62 degrees with the x-axis, and I want to know the gradient of that line. Well, when we're given the angle, that's when we focus our attention on the other form of the gradient. So that's when we focus on the fact that m equals tan theta, which means that 62 degrees in this case is going to be our theta. It's the angle between there and the x-axis, so counterclockwise up. which means that for my gradient, I have to do tan of 62 degrees. When you plug that in a calculator and you do it, what we end up getting is that m equals 0.62 to 2 decimal places. Okay, so we get a gradient of 0.62 for that line. We can figure it out fairly straightforward like that. We could also kind of turn the problem round on itself too. Imagine I tell you I've got 2 points. I've got a point P, which is at the point -2, -2, and I've got a point Q, which is at 1,7. And imagine I told you I want to know what angle the line PQ makes with the x-axis. So if I was to do a rough sketch of it, it would look something like that, and I want to know what this angle theta here is. Well, we know m equals tan theta, but we also know the original version of our formula, so we use that to begin with. So we'd use y2 minus y1, so 7 take away -2, over 1 take away -2. So in this case, we'd end up with 7 minus -2, so 9, over 1 minus -2, 3. What that then allows me to do is calculate the gradient. 9 divided by 3, that gives me a gradient of 3 for the line. Now, I can now at this point use my alternative version of the formula. I know that m equals tan theta. So what I now know as well is that m is 3. So I can use this to form a new relationship and say that therefore, obviously, tan theta is equal to 3. Use my inverse trig function, so m equals tan minus 1 of 3. Stick that in your calculator and get it. What you'll end up getting is that theta equals 71.57 degrees to 2 decimal places. What we're able to do is use that to create this relationship and find our new gradient using this new property we've got here. That's one property when it comes to the gradient of straight lines that we can use. Another property involves when we look at perpendicular lines. Now, a perpendicular pair of lines, so when we've got two lines that cross each other at some point, but the angle between them is 90 degrees. Perpendicular lines cross each other and meet at 90 degrees. So a pair of perpendicular lines like this will have a setup similar to this sort of equation, this sort of scenario here. Now, imagine I tell you that line 1 has a gradient of m1 and line 2 has a gradient of m2. So there's line 1, there's line 2. What this gives me is it gives me a property where if I take the gradient of the first line, m1, and I multiply it by the gradient of the second line, I get the same answer every single time, -1. So if I'm looking to find the gradient of a line that's perpendicular to one I already know, I can use this property. Or if I'm looking to prove two lines are perpendicular, I can use this factor as well. So let's have a look at an example of this. Imagine I have got 2 points. Let's say I've got a point T located at 1, -2, and I've got a point S located at -4, 5. And I want the gradient of the line that's perpendicular to these. First thing I'll do is find the gradient of TS. Do that using a normal standard formula. So we do 5 take away -2 over -4 take away 1. 5 minus -2, 5 plus 2 gives me 7. -4 take away 1 gives me -5. So my gradient there is -7 over 5. Now, if we were to call MP being our perpendicular line, we would know that MP times the gradient of TS is equal to -1. So what we know then is that the MP, our perpendicular gradient, is equal to -1 divided by the gradient of TS. We know the gradient of TS is this, so we know our perpendicular gradient is equal to -1 divided by -7 over 5, which is the same as saying -1 times -5 over 7. From this, our gradient of our perpendicular line, MP, is equal to 5 over 7. That's how we can use this property to calculate a perpendicular gradient of a line. We're able to say, this is how we do it. But again, it also allows us to prove two lines are perpendicular. So a normal scenario for something like this is, imagine I have 3 points. I'm going to tell you a point M is going to be at point negative 3, 9. A point O is going to be located at the origin. And a point P is going to be located at 12, 4. Imagine what at this point I would say is I want to show that this is a right-angled triangle at O. So what I'd want is, if you could imagine, I've got the points plotted here, I've got M here, I've got O here, and I've got P. I would want to prove that this can join up and create a little right-angled triangle where the right angle is located here. Well, in doing this, I would want to take this as my first gradient, this is my second gradient, and use the property we've just talked about. M1 times M2 is negative 1. So if I did M1 here, I would know it's the gradient of M to O, so use these points here. So I'd do 9 take away 0 over negative 3 take away 0. So that'd be 9 over negative 3, which is negative 3. I would then do my second gradient, the gradient of O to P. So in this case, I would do 4 take away 0 over 12 take away 0, which would give me 4 over 12, which is 1/3. I would then do the calculation of M1 times M2 equals negative 3 times 1 over 3. Lo and behold, negative 3 times 1/3, negative 1. Because my two gradients multiplied to give me negative 1, I'm able to say, therefore, it creates a right angle triangle, and O is where my right angle rests. These two key properties of gradients of straight lines are things that we have to be able to use quite openly and quite frequently within the higher course. So we need to remember the alternative way of calculating the gradient. The gradient equals tan theta, where theta is the angle made by the line from the x-axis up to the line in a counterclockwise direction. We need to remember the key property of perpendicular lines, where M1 times M2 equals negative 1.